Consider a vector r. If we multiply vector r by 2, we get another vector, 2r, with the same direction as vector r, but twice its magnitude. Similarly, if we multiply vector r by -3, we get another vector, -3r, opposite in direction to vector r and with thrice its magnitude. Note that in these cases, we have multiplied vector r with the scalar quantities 2 and -3 to get new vectors. If we multiply any vector, say vector r by a scalar quantity, say lambda, we get another vector, lambda r. The magnitude of vector lambda r is equal to the magnitude of the scalar quantity, lambda, multiplied by the magnitude of vector r. The direction of vector lambda r depends on the sign of the scalar quantity, lambda. The vector obtained by multiplying a given vector with a scalar quantity is collinear to the given vector. Now, let us take some special cases. Multiplying a given vector r by -1, we get vector -r, which is equal in magnitude but opposite in direction to vector r. Vectors r and -r are called additive inverses of each other, and their sum is a zero vector. Multiplying a non-zero vector r with the reciprocal of its magnitude, we get a vector whose magnitude is 1. In this case, the new vector is a unit vector r with the same direction as the given vector and magnitude equal to 1. A unit vector r is denoted as shown. The multiplication of vectors by scalar quantities follow the distributive laws shown here. Consider a three-dimensional coordinate system. Let P be a point in space with coordinates x, y, z. Let us draw a perpendicular PA from point P onto the XOY plane. Let Q and S be the feet of the perpendiculars drawn from point A to the X and Y axis respectively. Complete the parallelepiped as shown. Now, Q, S and R are the points on the X, Y and Z axis respectively, such that OQ is equal to X, OS is equal to Y, and OR is equal to Z. Now, vectors I, J and K are unit vectors along the X, Y and Z axis respectively. Thus, vector OQ is equal to X into unit vector I along the X-axis. Similarly, vector OS is equal to Y into unit vector J along the Y-axis, and vector OR is equal to Z into unit vector K along the Z-axis. From the figure, we have vector QA is equal to vector OS, that is, Y into unit vector J. In triangle OQA, vector OA is equal to vector OQ plus vector QA. Thus, vector OA is equal to X into vector I plus Y into vector J. Again from the figure, we have vector AP is equal to vector OR, that is, Z into unit vector K. In triangle OAP, vector OP is equal to vector OA plus vector AP. Thus, vector OP is equal to X into vector I plus Y into vector J plus Z into vector K. This form of vector OP is called the component form of vector OP. X, Y and Z in their component form are called the scalar components or rectangular components of vector OP. The scalar components of a vector are called its direction ratios. Xi, Yj and Zk in their component form are called the vector components of vector OP. Now, let us find the magnitude of vector OP. In right-angled triangle OQA, the square of the length of the hypotenuse OA is equal to the sum of the squares of the lengths of sides OQ, QA. That is, modulus OA square is equal to x square plus y square. In right-angled triangle OAP, the square of the length of the hypotenuse OP is equal to the sum of the squares of the length of sides OA and AP. Substituting the corresponding values, we get the magnitude of vector OP is equal to the square root of the sum of the squares of its scalar components x, y and z. Suppose vector OP makes angles alpha, beta and gamma with the x, y and z axis respectively. Then the direction cosines of vector OP are given by cos alpha, cos beta and cos gamma. They are denoted by L, M and N respectively. If the direction cosines of a given vector are known, then the unit vector in the direction of the given vector can be written as shown. Now, consider a vector A in its component form. Multiplying the given vector A by a scalar, lambda, we get another vector as shown. Now let us learn about some interesting relationships between two vectors, A and B, given in their component forms. To find the sum of two vectors, add the corresponding scalar components, as shown here. To find the difference between two vectors, subtract the corresponding scalar components, as shown here. Vectors A and B are equal if and only if their corresponding scalar components are equal. The given vectors A and B are collinear if and only if there exists a scalar, lambda, such that the component form of one vector is equal to lambda times the component form of the other vector. On simplifying, we find that the two vectors A and B are collinear if their corresponding scalar components are in a constant ratio. Consider 2 points P1 and P2 in space as shown here. Let us find vector P1, P2 by joining the two given points. Let us draw vectors OP1 and OP2 from the origin to the given points, P1 and P2 respectively. Applying the triangle law of vector addition in triangle OP1, P2, we have vector OP2 is equal to vector OP1 plus vector P1, P2. On rearranging the terms in the equation, we get vector P1, P2 is equal to vector OP2 minus vector OP1. Let this be equation 1. If vectors I, j and k are unit vectors along the x, y and z axes, respectively, then vector OP1 in component form is given by x1 into vector I plus y1 into vector j plus z1 into vector k. Similarly, vector OP2 in component form is given by x2 into vector I plus y2 into vector j plus z2 into vector k. Let us substitute the component forms of vectors OP1 and OP2 in equation 1. On simplifying, we get vector P1, P2 as shown here. The magnitude of vector P1, P2 is given by the under root of the sum of the squares of its scalar components x2 minus x1, y2 minus y1, and z2 minus z1.